So hello and welcome to the unit on permutations. We're going to start with lesson 1 today. We want to talk in general about organized counting principles, and really these next two units, permutations and combinations, are all combinatorics. And combinatorics is a branch of math that deals with ideas and methods for counting. Now counting seems pretty simple. You've been counting by adding and subtracting, multiplying and dividing, but when you try to count more complex scenarios, you hit a wall where you need to have more complex strategies to help you with that. So consider counting how many possible license plates there are in Ontario, or how many 5-card hands are possible with a standard deck of cards. You could sit down and try to figure out what all the different possibilities are and then count them up one by one. But we're going to teach you some strategies that you can use to count very complex scenarios like this. Often we can look at tree diagrams, we can look at lists or charts or even Venn diagrams to help us count the possibilities in a given situation. Sometimes those would be too time consuming, so we're going to choose other methods like permutations and combinations, units 1 and unit 2 here, to perform the calculations.
So because we're focusing on permutations, we should define what permutations are. And permutations allow us to count how many arrangements can be made with a certain number of items when the order of those items is important. Okay, so certainly in a license plate, the order of the letters and the numbers are important because they distinguish one license plate from another license plate. You know, a license plate that starts with BBMY is a different license plate than BMBY, right? It gives a different characteristic to that license plate. So permutations really are arrangements of certain objects where order is important. Combinations allow us to count how many selections can be made when order does not matter.
Mm-hmm.
So when you're playing, maybe a card game and you've got a king, a queen, a 5, a 2, and a 3 in your hand, it doesn't matter what order you hold those cards in your hand.
No.
Just the fact that they're in your hand is all that really matters. So the order of those cards does not matter. And that is what distinguishes permutations from combinations. What we're going to do is we're going to divide these two concepts into our first two units. And we're going to consider them separately, and then at the very end we'll come back and we'll consider them together and how to distinguish between them. Basically, what we're looking at is that this field of study, combinatorics, provides us with systems and techniques that we can use to calculate the possible outcomes in very complex situations. This math really relies not on heavy algebra or arithmetic or formulas. It relies on logic and two basic counting principles. You'll know that to try and build your logic base in these problems, exposure to a lot of examples is going to be very important. And so throughout these units, you will see lessons with 6, 7, sometimes 8 different examples to give you as much exposure to the type of logic that we're using to count as possible.
And you really are going to be using mostly adding, multiplying, and subtracting.
Yeah.
And then once we get into probability, you'll start dividing because you'll have a denominator and a numerator. But we're going to use the math that you learned in grades 2 and 3, but we're going to combine it with your grade 12 logic.
Yeah, to really hit home what we're talking about here.
Yeah. So let's start by looking at, what happens if you need to make a series of choices at different stages. So you've got stage 1, you got to make a choice. Then you move to stage 2, you make another choice. You move to stage 3, you make another choice. What we want to do is we want to figure out how many possible paths are there. So how many you can imagine as though there are different alternate universes. If you'd made all these different choices, how many possible little alternate universes would there be for this situation? So we call that the number of outcomes or the number of paths. So we can probably start with an example to kind of give you a picture of how that looks. So let's pretend Bob wants to have breakfast. He's got options of tea, coffee, and orange juice to drink, and he definitely wants something to drink. He can have eggs, cereal, or pancakes for his main, and again, he definitely wants to have a main, and he can either have toast or hash browns as his side, which he also wants. We've assumed that he wants all of those, Okay, so how many breakfasts could he choose from? We're going to set it up and we're going to look at it in terms of stages. Okay, if we make a tree diagram to visualize all the outcomes, this is one of the organized counting strategies that we can create as a tree diagram. And once we've created the tree diagram, if we count the number of leaves at the end of the tree, the number of final values at the end, that tells us how many paths or outcomes there were that he could have had. So we know that he wants to start with a drink, right? Then we know he wants to follow that with a main, and then he's going to choose his side. So when we go to the drink, we say, okay, Bob, you got 3 choices. You can either have tea, you can have your coffee, or you can have your orange juice. Let's pretend he chooses tea. So he's got 3 choices in stage 1. Let's pretend that Bob chooses tea. So from tea, he still has his mains that he can decide on. He can have eggs, he can have cereal, he can have pancakes. And so from the tea choice, he's got 3 paths: eggs, cereal, and pancakes. Now he has those same 3 paths from the coffee choice and from the orange juice choice. So stage 1, we had 3 choices. Stage 2, we also had 3 choices, but they compound so that each of the first choices in stage 1 gets its own 3 different choices in stage 2. From those, so let's say he chose tea and eggs. So we'll go right up there to the top. Now he's got his tea, he's got his eggs, he wants a side. He can either have his toast or his hash browns. Okay, so those are his 2 more choices, 2 more paths. From tea and eggs, you have 2 more paths to hash browns and toast. But from tea and cereal and tea and pancakes and coffee and eggs and coffee and cereal and coffee and pancakes, from all those other paths, he also has all those other 2 choices of hash browns and toast. Okay, so once we get to the end and we sit here and we count all of these leaves at the end, all this hash brown toast, hash brown toast, hash brown toast, all the way down, well, how many possible paths, how many possible outcomes could Bob have had for breakfast? Turns out that he has 18 total breakfast choices because if you count, there are 18 leaves or 18 terminal points on this tree diagram. Notice how we set it up where we put stage 1 at the top or first, then stage 2 after it, and then stage 3 after that. And then vertically, we listed the choices. So we're building this tree sideways instead of up and down.
Yeah.
Okay, just because it's a little bit easier to write, it takes up less space. Yeah. And we can think of it as first, second, and third stages.
We talk about paths because there's a certain number of ways that we can navigate through all of these different there's a certain number of ways that we can navigate through the tree. From coffee to cereal to toast is a different path than coffee to from coffee to pancakes to hash browns. They're all different paths that you can take, and those represent different choices you can make. And here we have a lot of writing in here. And so very often what you'll see in tree diagrams, and what we would encourage you to do, is create a code for how you're going to do your
yeah, like T, C, O, J, E, C, P, H, T, right? Yeah. For your egg, cereal, and pancakes.
So kind of create a code so that you're really minimizing the amount of writing that you have to do, because this would be quite a bit. Shifting. Let's look at another example that uses the same kind of strategy.
Yeah.
So Deidre wants to purchase a new car, and so when she goes into the dealership, she has some choices that she needs to make. She can have a choice of either a 2-door car or a 4-door car. She can have the choice of a standard transmission or an automatic transmission. And finally, she can have the choice of either a red exterior, a white exterior, or a gray exterior. And so what we want to do is use a tree diagram to determine the total different number of selections that she might have when she's choosing a car. And so what we want to do here is, of course, we set up our different stages, right? So first we're gonna look at the doors. Then we're gonna look at the type of transmission. Then we're gonna look at the color of the car. And so underneath doors, we have 2 choices. We have either a 2-door car, or we have a 4-door car. Okay, and from here we say, all right, well, if we want to look at transmission, we choose a 2-door car. We have either a standard transmission or an automatic transmission, and this represents 2 separate paths. Okay. We have the same choices if we choose a 4-door car. We can either have a standard transmission or an automatic transmission. Okay. Then when we look at color, if we choose a two-door and with a standard transmission, we've got the choice of gray, white, or red as our color of the exterior. Well, we have the same color choices then for all of these other branches. And this represents, of course, a whole bunch of terminal points of this tree diagram. And we've got 3 here, we've got 3 here, we've got 3 here, and we've got 3 here. So the total number of card choices that we have is 12. Mm-hmm. Now, let's take a look at an interesting pattern that we see emerging from this scenario. If to reach a desired outcome, we need to make a first choice and a second choice and a third choice, then we multiply the number of choices at each stage to get the total number of outcomes. So it just so happens here that we have 2 choices in our first stage, we have 2 choices in our second stage, and we have 3 choices in our third stage. And when we multiply these together, we get a total of 12. And that's not a coincidence that this has turned out this way. This is actually a concept, and it's the first of your 2 counting principles. This concept is the fundamental counting principle. And it's an important principle because it basically says that if a task or a process is made up of stages with separate choices at each stage, the total number of choices is m times n times p, where m is the number of choices in the first stage, n is the number of choices in the second stage, p is the number of choices in the third stage, and so on and so forth.
And this makes sense because you're compounding at each stage.
Yeah.
You're compounding the number of choices that you have, and so that compounding is a multiplicative factor, right?
Yes.
Now, you also might see it called the multiplicative counting principle, but we're going to refer to it as the fundamental counting principle. We'd like you to refer to it as the fundamental counting principle. And in fact, on tests or on a problem set or on an in-class challenge, we will definitely be asking you to explain what it is, when you can use it, how it works. Okay, so this is something, we've put it in these fancy boxes, right? Because we want you to make sure that you note what it is, how it works, and what it's called.
Okay.
All right, so let's say in your first year of university, you get a co-op job for the summer, which is a yay. This job, though, requires you to dress professionally each day. For some of you, maybe a boo. You do not have a lot of clothing that suits your purposes right now. Now, you're in first year university, you don't have a lot of money, you don't have a lot of outfits, but you do, however, have the following items in neutral colors. Okay, you've got 4 different shirts, 3 pairs of dress pants, 5 ties, and 2 pairs of dress shoes. Again, neutral colors. If
they're all neutral,
they're
that
all
means
neutral.
they all match.
That means
right?
they match. That's what we're gonna say, because they're neutral. That means they match. Okay. If you must wear a shirt and a tie and pants and shoes. Okay. So the pants are not optional.
No.
Not at your professional job. But okay, let's say no one's looking at your socks, so who cares what you're wearing? You may not even wear any socks. How many possible outfits can you create to tide you over until you get your first paycheck from this co-op job and you can buy something that maybe looks a little fancier? All right, so we know that there's a shirt stage. You've got to choose from one of your 4 different shirts. Once you've chosen a shirt, you move to the pants stage. Then you move to the tie stage, and then you move to the shoes stage. So it's the same as we were looking at there. If you wanted to make a tree diagram, you could. You'd have your shirts, your pants, your ties, and your dress shoes, and you'd make your branches. But what happens is, as the numbers get larger and larger, the tree diagram becomes less and less functional. It takes up more space, takes too long, and we have the fundamental counting principle, so we don't need it anyway. So basically, we're going to multiply the choices at each stage by each other because they compound in order to find out how many possible outfits we can make. So this notation, n bracket outfits, end bracket, it says the number of possible outfits, or the number of outcomes for your outfits is. And we're just going to do 4 times 3 times 5 times 2, because we've got our shirt stage, our pants stage, our tie stage, and our shoe stage. And then we get a total of 120 different outfits if we must make a choice at each of those 4 stages. We can't choose not to wear pants to work.
Yeah, exactly.
Okay.
Now, if you think about what a tree diagram for this would look like, it would be huge. It would be huge. 120 terminal arms. And so that's why tree diagrams are a great strategy when the numbers are small.
And to help you get a conceptual understanding of why you're multiplying each of these.
Yeah.
Okay, so it helped you build, and it will help you in some very complex questions. You're going to go to a tree diagram as your first choice to help you reason things out. But yeah, the numbers start to get really big. Yeah. All right, so what if your supervisor is a little more flexible and says, listen, you can wear your tie or you cannot wear your tie. Okay, so they're going to give you the choice of wearing the tie to work or not wearing the tie to work. So with the tie, which is from example A above, we know the number of ways of putting on this outfit with a tie included. So there's definitely a tie stage is 120. Now, if we have the choice of not wearing the tie, then that means we essentially remove the tie stage. So now we're only making choices at 3 stages.
So we're only choosing between shirts, pants, and then shoes.
Okay, so we've removed that whole column from what would be our tree diagram. So the number of ways without the tie will just be 4 times your 3 times your 2. Okay, so we've removed those 5 ties, which gives you 24 different outfits without the tie. Okay, so the ties actually give you a lot more variety in your wardrobe. But here's the thing. Since you can't simultaneously wear a tie and not wear a tie at the same time, these events are considered to be mutually exclusive. Okay, so mutually exclusive events would be events where there is no overlap. You can't both do it and not do it at the same time. And because these events are mutually exclusive and they're both desirable, we can just add their outcomes. We can say, well, I could wear the tie or not wear the tie. So I have these 120 options, or I have these 24 options. And there are 2 important concepts here. One is the concept of something being mutually exclusive. They cannot occur at the same time. The second is what we're going to look at called the additive counting principle. So if we take the number of ways with the tie and add it to the number of ways without the tie, then really the number of ways of making an outfit with or without a tie is simply the sum of the number of ways with the tie and the number without the tie. Okay, so this combination here of adding those 2 possible outcomes is the additive counting principle. You may also read it in university textbooks too, is referred to as the rule of sum, but we're going to refer to it as the additive counting principle. And it essentially states that if one mutually exclusive event can occur in m ways, another mutually exclusive event, so there's no way the 2 things can happen together, is in n ways, another in p ways, and so on, then the total number of ways that these can occur is m plus n plus p. And what you'll see is the word or is the cue word. That you can wear this or that means that I would like these or those, so any of them is good, so then you can sum them together. Okay.
And is also a key word for the fundamental counting principle.
Yes.
When you wear this
and
this
one of these and one of these,
then you're looking at the fundamental counting principle.
Where
and
you're
so
multiplying.
The distinction between the words and or is one of those things where all of a sudden you're going to start cueing on certain little things in problems where you can say, oh, okay, this is telling me that I can either do this or I can do this. And so I'm going to be considering the additive counting principle. All right, so let's take a look at a good example of this. In any standard deck of cards, there are 52 cards that are all individual, and they're grouped into 4 different groups called suits. Okay, clubs, spades, hearts, and diamonds. So knowing this, we want to say, okay, well, how many ways are there to select a card that is either a red face card or a black ace? Okay, so let's go over what the red face cards are. Face cards are any card that has a face on it. So a king, a queen, or a jack. And so these 6 cards right here represent the red face cards. These 2 cards represent the black aces, which is the ace of clubs and the ace of spades. And so if I have a whole set of cards and they're all laid out on the table and they're shuffled, how many ways could I reach into that shuffled mass of cards and select a card that's either a red face card or a black ace? So the first thing that we need to ask ourselves is, are these 2 things, a red face card or a black ace, are these mutually exclusive? And we know that there's the word or that's coming in here, red face or a black ace. And so there's a couple things that are being thrown at you here. We say, all right, so because we see the word or, we know that we're probably going to be using addition and the additive counting principle. So now we have to say, all right, are these two events mutually exclusive? I.e., is there any way that I could reach into this shuffled mass of cards
Yep.
and pull out a card that happens to be a red face
And a
black
simultaneously.
ace simultaneously? But there's no card that fits that criteria because a card cannot be red and black at the same time.
Yeah.
So these then are mutually exclusive events. And because they're mutually exclusive, we're going to use the additive counting principle to solve. So we say, okay, well, there's 6 ways that we could reach in and pull out a red face. And there are 2 ways that we can reach in and pull out a black ace. And so 6 plus 2 is 8.
Yeah.
Okay. So going on to part B. How many ways are there that we could select a red face card and a black ace, one after the other?
Now this is key because notice how in part A it said a card, one card, and that card is either a red face or a black ace. So that in your hand you have only one card. There's only one stage.
Yes,
it's
one
just
stage.
that there are different options for that stage that are mutually exclusive, so you can add them together. Here, if we want to take a red face card and a black ace, one after the other, then that means there's two stages. Yeah.
And we're actually taking 2 cards.
Yeah.
So this right here, one of the key words that we look at is this right here, which is and. And it's different. We had a red face or a black ace in example A, and here we have a red face and a black ace, one after the other in example B. So in this case, this is a cue to say we're going to be using the fundamental counting principle. So the number of ways that we can select a red face card and a black ace card is 6 times 2, which are 12 ways of selecting these one after the other.
Yep.
All right. So now we come to part C, which is how many ways are there that we could select a a heart or a queen?
Yep.
And so we need to say, okay, well, we see the word or there. Right? We see the word or.
So we're thinking
we're going to be adding at some point, right? So that's one thing that we're going to think. But we need to ask ourselves, are these 2 things mutually exclusive? Can you reach into a deck of cards and pull out a card that happens to be a heart and a queen?
Yeah.
And the answer in this case is you can do that.
Yeah.
So these 2 events, the event of pulling a heart and pulling a queen, are not mutually exclusive because they can happen at the same time.
Yeah. Now there are hearts that are not queens.
Oh yeah.
And there are queens that are not hearts.
Yeah.
But because we do have that one queen of hearts,
yeah,
there is that overlap. There would be an overlap in a Venn diagram there. And so we can say that, yeah, this is not mutually exclusive because you can simultaneously be a heart and a queen at the same time.
And so when we're counting the number of ways that we can select these cards, we have to make sure that we don't overcount.
Yeah.
We have to keep that in mind.
Yeah.
So here's what we're going to do. We're going to say, okay, first of all, how many hearts are in the deck that are not queens?
Well, there are 13 hearts altogether,
yeah,
but one of them is the queen of hearts.
So we want to subtract that out,
yeah,
and we want to keep track of the number of hearts that are not queens. And so 13 minus 1 is 12. There's 12 hearts that are not queens. How many queens are in the deck that are not hearts?
Okay, well there's 4 queens altogether, but one of them is the queen of hearts.
Yeah.
So there's only 3 queens that are not hearts.
Yeah. So here we have, there's the one heart that happens to be a queen. And over here, here are the other queens that are not hearts. So if we had simply counted, okay, how many hearts are in a deck? Well, there's 13. How many queens are in a deck?
4.
4. And we had added those 2 numbers together.
We'd say, oh, there's 17 ways.
There's 17 ways.
Sure.
But of course, this little guy right here in the middle, the queen of hearts, we would, of course, double counted.
Twice. Yeah.
So we would have counted it in the heart section. We would have counted her in the queen section.
Yeah.
We would have counted her twice. And so that's why we need to separate into these 3 different cases.
Yeah.
So what we get, 12 plus 1 plus 3, again, or is our signal that we're counting here. Because we're still only choosing one card. We're not choosing cards at different stages. Yeah. we have 16 correct options.
Yeah. All right, so let's look at an example now where we use numbers. Okay, so we'll get away from deck of cards for a second. We'll say we're going to use the digits 1, 2, 3, and 4. So imagine you've got 1, 2, and 3, and 4, and they're on little wooden tiles like Scrabble tiles or something like that. And we want to know, okay, using those 4 numbers, using those 4 tiles, allowing for repetition though, how many different 2-digit numbers are possible? Okay, so really what we've got is we've got 2 stages. We're going to choose the first digit, and then we're going to choose the second digit. And because we have 4 numbers to choose from and we're allowed to repeat, then we really have 4 different choices for the first digit or for the first stage. Okay. We also, because we're allowed to repeat, when we move to the second stage and say, okay, now I'm going to choose the second digit, we also have 4 choices for that second stage. So since we're making choices at 2 different stages, we want to have a first digit and a second digit. Okay? So notice how there's a little bit of self-talk going on here. It just says 2-digit number. There's no or, there's no and. Okay? But I know that if it has to be a 2-digit number, then I need a first digit and a second digit. I can't have a first digit or a second digit for it to be an actual 2-digit number. So in the way that I'm rephrasing the question to myself, I'm including the word and. That means that we're going to multiply these.
Yeah.
Okay, so 4 choices in the first stage and 4 more choices in the second stage gives us 16 possible 2-digit numbers if we're allowed to use the numbers 1, 2, 3, and 4, and we're allowed to repeat them. Okay, now what if we want to know, well, how many different 3-digit numbers are possible? Very similar.
Same method.
Yeah.
Same method. Yeah.
The number of 3-digit numbers that are possible, you're going to choose a first digit and a second digit and a third digit. You need all 3 digits, so there's 3 stages. Because there are 3 stages, 4 choices at each stage, we're going to do 4 times 4 times 4. So the number of possible 3-digit numbers is 64. How many different 2-digit or 3-digit numbers are possible? Well, we see the word or, and since you can't simultaneously be a 2-digit number and a 3-digit number at the same time.
Yeah, there's no such thing.
There's no such thing, so they're mutually exclusive. Okay, so when we see the word or, and we know we want to add them, we can only add them without reservation if we know they're mutually exclusive. And I know you can't be a 2-digit and a 3-digit number at the same time. So I can take my 16 different ways of getting a 2-digit number and my 64 different ways of getting a 3-digit number, and we can just add them together to get 80 possible ways of being a 2 or 3-digit number.
Okay. So now, though, instead of restricting ourselves to the numbers 1, 2, 3, and 4, let's use all of the digits from 0 to 9.
Crazy,
so that's 10,
crazy, Mr.
that's
Jackson.
10 possible
10 different
digits.
Yep.
Okay, so that's what we have to choose from. And what we're going to start doing now in this example is that we're going to start stacking what we call restrictions on the most basic way of counting. Then we're going to start restricting you. And we're going to say, okay, you need to make sure that this is included. This is a restriction.
Yeah.
So let's walk through this example now. We're still going to take 3-digit numbers. Okay.
And we're still going to allow for repetition.
Yeah.
So we could repeat numbers.
Exactly. So we've got the numbers 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to choose from. Repetition's okay. We only want 3-digit numbers. So we're going to introduce a way of kind of looking at how might be a good way to solve this.
Yeah. Yeah.
So let's create 3 spots. We've got 3 spots where we can put some digits.
Yeah. 3 stages.
Okay, so 3 stages. In the first stage, we're going to put our first digit, the second stage, our second digit, and the third stage, our third digit. Okay? In this first spot right here, how many numbers do we have to choose from?
Well, we have 10 digits. We have 0 to 9, so we have 10 possible values we could pop in, but we're going to give you a blanket restriction on any n-digit numbers without any kind of context. If we just say, here's an n-digit number, the rule is the first digit can't be 0.
And the reason for that is because if this was a 0, let's say I had 0, 1, 2, that isn't a 3-digit number.
It's really just 12.
That's 12. That's a 2-digit number.
Yeah.
So what we do is, if we're talking about 3-digit numbers, how many choices do we have to fit in this first spot? We have 9. And that's because we can't use a 0 in this first spot.
So imagine that you took your 10 digits and you just flicked the 0 out. Yeah. So that now all you have left in front of you are 9.
Yeah.
Okay.
So there's 9 choices to go in this first spot.
Yeah.
We're going to multiply that by, well, how many choices now do I have for the second number? Now I can use 0.
We can use 0, yeah.
And so I have all 10 choices for this digit right here.
Yeah.
And of course, for the third digit, I can use 10 as well.
You can use 0 again, yeah.
So the number of 3-digit numbers that are possible, if we're allowed repetition, is 900.
Yep.
Okay. So let's add another restriction. And this is one of the most common restrictions you'll see. Okay, now you're not allowed to repeat digits. So the number 111 is not acceptable in here, right? So basically, the number of 3-digit creations that we have without repetition, well, let's set it up in the same way. Okay, here's our 3 spots for our 3 different digits. Again, how many choices do I have for that first digit?
Well, we would have 10 different choices, including the 0, but we know that we don't want to include 0 for the first digit. So we remove 0, leaving us only 9 choices for the first digit.
And again, if it's a 3-digit number, can't use 0 first. You're going to see this all the time, right? So get very used to saying, oh yeah, I can't use 0 in this first spot. Okay, now the second digit comes along, and we need to make a choice here. Can I use 0?
Yes.
Can I use the number that I used first?
No.
Because repetition is not allowed.
Okay.
So if I add 0 back into the 10 digits I have to choose from, but I subtract the 1 off, whatever it was that I used in the first spot, I'm still at 9. Right? And the reason I'm still at 9 is because here we can use 0, but we can't use the first number.
Yeah. So we've lost a number.
Yeah, so we're down to 9. How many choices now do I have for this digit?
Well, it's interesting because we've put a number in the first digit position, and we've put another number in the second digit position, and now there's no restrictions on zeros or anything in the third digit, but we have already used up 2 numbers that we're not allowed to reuse.
Yes. So my options are now limited to the 8 remaining digits that I have that I've not used. And so when we multiply these together, now I get 648 3-digit numbers where repetition is not allowed. All right, so this last one is a little bit more of an extension. How many 3-digit numbers are possible that contain at least 1 5? So again, now repetition obviously is okay.
It's allowed. It's implied because they've said at least 1 5. So we could have 1 5 in there, we could have 2 5s in there, or we could have all 3 5s in there.
All right, so what we'd like you to do, because we're coming to the end of this lesson here, is considering that repetition's okay, devise a plan for how you might organize your counting and say, okay, I get 3-digit numbers, I need to include at least 1 5. So that means I could include 1 5, or I could include 2 5s, or I could include 3 5s. So given the sentence that we just read and this problem, try this one for yourself. Okay? The answer, just so that you can check, is 252.
Yeah. So bring your answer with you. Bring your solution that you tried it with you to class, and then what we'll do together is we'll go through the different solutions because people will have different methods they use to get this 252, and we'll talk together about how to set this problem up, which is really kind of 3 different problems in one.
And there's your introduction to organizing.